Hi, Mike here. We have been persuaded to believe that every star in the cosmos has a preset quantity of fuel that it burns through its lifetime. They say eventually the sun will explode into a supernova. And you know what else? That all of this is still only a theory. But you know what they're not considering? An equation that's part of a sequence of facts culminating into a realization that all astronomical bodies grow. The science consensus dictates that the sun will someday use up its existing fuel. Well, I'm here to inform you that there might be a problem with this existing fuel hypothesis. To quickly summarize, slowly but surely through the millions and billions of years that it has to accumulate the substance of what other stars are exuding, the sun soaks up everything that the universe is blasting toward it. This is an observation I am making as evidenced by other stars which make the sun a rather small star in comparison. Our star is an infant star. Many other stars are quite bigger as they would have a lot more time to become that way. My conjecture here is that it always has been and it will continue to grow until another force acts upon it. If the sun would ever explode into what's known as a supernova, it won't be doing it because it's used up its fuel. Why is that? It's because the sun is consuming a virtual limitless amount of fuel. It's getting more all the time, every day, and in more than one way. But today we're just going to talk about one. Now this may be in line with an Occam's razor, but a star may only go into supernova when another body of appropriate mass collides with it. It's been proposed by scientific communities that supernovas only happen once every 50 years per galaxy. Let's look at that mathematically. How many galaxies are there? Recently, with the use of the Hubble telescope, it's been estimated that there are approximately 100 billion galaxies in the observable universe. While that number is likely to at least double as telescope technology improves, let's just use that as a basic round number. It's also estimated that there are approximately 400 billion stars in our own galaxy, and that there are most likely as many or more in every other galaxy, but let's just use 100 billion as a base number within the following equation. Let's take 100 billion galaxies times 100 billion stars. That equals 10 sextillion stars. That's a 1 followed by 22 zeros. We are about to find out, using this equation, that there would just happen to be a lot more supernovas happening all at the same time. If an average of only one supernova happened every 50 years per galaxy, then you would simply divide 100 billion by 50 to get the number of supernovas that would just happen to work out to approximately 2 billion stars per year going supernova within our observable range. 2 billion divided by 365 days equals more than 5 million observable supernovas occurring every single day. That's more than 200,000 observable supernovas occurring per hour, which also works out to approximately 3,000 supernovas occurring every single minute, or 50 supernovas occurring within our observable part of the universe every single second. Now, since scientific data has concluded that a supernova is much brighter than the entire galaxy that it's exploding within, one can imagine that there would be quite a light show happening every single night as we look out into the night sky. In fact, to find any supernova occurring at all is quite a rare occurrence. We're still talking about hundreds of billions of stars per galaxy. And if, within those hundreds of billions of stars, only one goes off every 1,000 years, may not cut down the number far enough to lead us to believe that it is due to what should be more of a common occurrence because of a regularity, the running out of fuel. The theory that supernovas occur when existing fuel in a star runs out, linked with the Big Bang theory, sets in motion that everything happened all at the same time, should dictate that everything falls within some type of geometric pattern. This pattern of a star using up its fuel should be more common, hence at least once every 1,000 years per 100 billion stars, you would think. But what if it's every 10,000 years? What if it's every 20,000 years? What if it's every, not 50 years, 50,000 years? 200 billion divided by 50,000 years divided by 365 days divided by 24 hours divided by 60 minutes divided by 60 seconds, and that's just not happening. Could supernovas be actually that rare for a star running out of fuel? Or, while there are so many much bigger stars, could they be much more rare than that for another reason? If I'm wrong, I'll stand to be corrected, but as of yet, I think the latter is the case, and I'll explain why I think this is. The foundation of my conjecture is how all astrological bodies grow. If the sun is getting bigger, well, then possibly so is the Earth. The obvious indicators that the Earth is getting bigger is, by the way, all the continents fit together on all sides, while it's also demonstrated by its quantitative growth rings made visible by satellite imagery and what has so far been the scanning of most of the ocean floor by marine scientists. Just look at Google Earth! Such growth rings visibly stem from an ever-erupting stretch of oceanic plates that form a ring of eruptive matter encircling the entire planet like the stitches of threads on a baseball. Now, let's just use a little logic here and recognize that nothing actually grows without it consuming something. Every living thing has to digest something in order to get heavier and bigger, as far as we know. Something has to be added to it. Now, some people even consider the Earth as a living thing. I wonder why this is. The question is, what could the Earth be consuming to make it grow? I'll tell you my theory. Is it growing from particles being added to the outside only, as from mostly micrometeorites? Or are there particles that are being consumed by the Earth which go right through the surface of the Earth, which zoom right past the Earth's crust and into its core? We know that gravity is a force that pulls to the center of all matter, but have you ever heard that freed neutrinos seek planetary cores? Well, neither have I. So, let's get back to the sun. Some renowned space science buffs say that the sun is a fast-burning, extremely hot fire of exploding atomic charges with the bulk of its fuel recirculating at its core. In fact, all of them say that. They profess that when these explosions occur at the core, they emanate outward and inward and outward and inward and outward at a rate which takes about 1 million years before such exploding particles reach the outer layers. Once they reach the outer layers of the sun, they blast out through the surface of the sun to be lost into the vacuum of space. The blasting part is called solar wind. And is this still only considered a theory by just about everyone in the entire world's Astrophysical Scientific Society? This is the consensus that our solar system, not unlike most others, began as everything within the center of a massive dust cloud converged by a gravitational force within its center, eventually creating a star which eventually ignited. This ignition blasted particles away from itself, clearing the way within the entire solar system, while larger particles continue to converge together, forming planets, of which each of their own gravitational pulls sucked in their own surrounding orbital matter, creating what we have now, with the planets orbiting the sun, leaving not much left in between. If this condition is a framework for the production of solar systems, then it would logically create such a condition, which is the consensus of the world's view, that the sun, as well as most other stars, must have a limited fuel supply. Logically, through the eyes of a Big Bang theorist, this might be a logical scenario, but I have to argue with this because of the point of view regarding the growth equation. First, let's take a look at the way the sun is radiating its solar wind. From what is now available in high-definition imagery, it appears the sun is steadily erupting flows of boiling fiery soup at its surface, with magnetic fields appearing to hold the flows down at the surface. Quite often, surface flow patterns become unstable and break free from the magnetic field lines to violently spread out toward vast reaches of outer space. Sometimes they race toward Earth. They're called coronal mass ejections, and when they're big enough, Earth feels it. When a substantially large set of Earth-directed coronal mass ejections happen, it takes about 24 hours for them to travel through space before they hit the Earth. When they do, it's typically known now that they cause earthquakes and substantially more volcanoes to erupt. It's been my observation that it can take a long time for these enormously massive waves of ejected particles from the sun's corona, after they arrive to the Earth, before the Earth shows us how severely it's been affected. It can take quite a long time. The time variables are yet undetermined. What doesn't take long, however, is how CMEs immediately affect scientific equipment. Spacefaring equipment within Earth's orbiting satellites can fry to a crisp. And what exactly is it that plunges toward the Earth from the Sun? Some say it's ionic particles, while others say it's an array of heavy metals, like copper, zinc, lead, iron. When the colors of the northern lights give way, they display the same spectrum that heavy metals emanate when they're burned. It's believed that these heavy metals from the Sun burn through the upper atmosphere. Where do they go when they burn through the Earth's atmosphere? Do they fill the atmosphere with toxic heavy metals? Or might they be so small and traveling so fast that they can enter into the Earth's crust, or even pass through it? And what about neutrinos? Nearly massless particles that shoot out from every atomic particle that splits within the core of every star, including our Sun. The science consensus tends to theorize that these particles are so small yet so dense, while being so light, that they pass right through entire planets. Others might conjecture that some neutrinos may shoot directly into planetary centers without passing all the way through. If both neutrinos and solar wind materials both enter the Earth's crust, it might be logical to assume that this type of transfer of materials is somehow digested in the Earth's core, adding to its density, in effect together heating the planet and making it grow. The larger the planet, the faster the growth rate. The Sun would also have the same capacity to consume matter the same way the Earth would, while every star in the galaxy is bursting materials outward and toward one another, while every single galaxy is doing the same. I should insist that this is not the only way that planets and stars grow, but with this postulation, it should then be apparent that the Sun soaks up more intergalactic radioactive matter than the Earth can due to its much bigger size. Of course, this is conjecture on my part, but I'm just using a little bit of reasoning through the growth equation. We're talking about the Earth, and is it any coincidence that all the continents fit together on all sides, as would to apportion a much smaller planet? And lastly, I'm introducing these controversial points of view so that you might delight in trying to figure them out, as we will be in our next following episodes of Astrophysical Controversies.